Today we're going to be looking at Unit 3, Lesson 5, Indirect Proof. So we got some key concepts on how to write an indirect proof. So we're going to be following through these 3 steps as we write our indirect proof. We have 3 vocabulary words that you need to define, so make sure you take a look at your vocabulary sheet to see what the definition is for each of these. So let's take a look at example 1. Example 1 says write an indirect algebraic proof. So write an indirect proof to show that if negative 4x minus 4 is less than 12, then x is greater than negative 4. So we're given negative 4x minus 4 is less than 12. We want to end up with x is greater than negative 4. So we want to start with making an assumption. So the negate of x is greater than negative 4 is, so let's put step 1. So to negate that, we're going to say x is less than or equal to negative 4. So what we're doing is we're assuming that x is less than negative 4 or that x is equal to negative 4 is true. Step 2, we want to contradict this hypothesis. So step 2, we want to contradict this idea. So case 1, we said x equals negative 4. So when x equals negative 4, we have negative 4 times negative 4 minus 4 would equal 12. But we don't want 12. We want 12 is less than 12. We got 12 equals 12. That's not what we want. We want 12 is less than 4. Our other way we said was x is less than negative 4. So if we plug that in, we would also end up with a contradiction. So x is less than negative 4, that would be like negative 5, which would give us negative 4 minus 5 minus 4 would give us 20 minus 4, which is 16. But again, 16 is not less than 12. So that is also a contradiction. So in both cases, the assumption leads to a contradiction of the given information. So step 3. Therefore, the assumption that x is less than or equal to negative 4 must be false. So the assumption that x is less than or equal to negative 4 is false. So x is greater than negative 4. So this is called proof by contradiction. Let's take a look at example 2. So we want to apply indirect reasoning for example 2. Marco hikes more than 10.5 miles on a path, making just 2 stops along the way. Use indirect reasoning to prove that he hiked more than 3.5 miles on at least one leg of his hike. So our given is he starts off the hike, he makes a stop. He does more of the hike, he makes a second stop. He does the rest of his hike for all this totaling more than 10.5 miles because he hiked at least 10.5 miles. We want to prove that x is greater than 3.5 or y is greater than 3.5 or z is greater than 3.5. Basically, on one point of this trip, he went more than 3.5. So again, step 1 is make the assumption. So we want to prove that he went more than 3.5, so we're going to assume the opposite. He went less than or equal to 3.5 or y is less than or equal to 3.5, or z is less than or equal to 3.5. So we're making the opposite assumption here for step 1. Step 2, we want to contradict the hypothesis. So if x is less than 3.5, y is less than 3.5, and z is less than 3.5, then x plus y plus z is going to be less than or equal to 3.5 plus 3.5 plus 3.5. Or x plus y plus z, adding all this up, 3 plus 3 plus 3 is 9. 0.5 and 0.5 will give you 10, plus another 0.5 will be 10.5. So we're saying that he walked less than or equal to 10.5. But that's not true because it tells us that he hiked at least 10.5. So he hiked greater than 10.5. So again, we have a contradiction right here. So this doesn't work. So step 3. As I said, this is a contradiction of that given statement. Therefore, the assumption is false. So false that x is less than or equal to 3.5, y is less than or equal to 3.5, or z is less than or equal to 3.5. Marco traveled more than 3.5. So Marco traveled more than 3.5 miles on one part of his trip. So again, you start off with the opposite. You show that it cannot work, and therefore it makes a false statement. So since it's a false statement, then the other thing has to be true. So let's take a look at example 3. So indirect proof in number theory. So write an indirect proof to show that if x squared is an odd integer, then x is an odd integer. So given x squared is an odd integer, prove x is an odd integer. X is an odd integer. So assume that x is an even integer. To assume that x is an even integer means that x equals 2k. So assume x is even. So x equals 2k. So we're going to rewrite x squared in terms of k. So we have x squared equals 2k squared. Well, 2k squared is going to be 2k times 2k, which is 4k squared. Or in other words, we can have 2 times 2k squared. Because k is an integer, 2k squared is also an integer. So what we're going to do is we're going to let n represent the integer 2k squared. So x squared can be represented by 2n. So let n equals 2k squared. So x squared equals 2n. This means that x squared is an even integer, which contradicts the given statement that x squared is an odd integer because the assumption that x is even leads to a contradiction of the given. So this will tell us x squared is even. And that's not what we want. The original conclusion, x is odd, must be true. So false. We know x squared is odd. So x is odd. And there you go. So again, you want to assume the opposite, and by assuming the opposite, you prove that it can't be that. So since it can't be that, then therefore what we originally wanted to prove is true. All right, example 4, write an indirect geometric proof. If an angle is an exterior angle of a triangle, prove that its measure is greater than the measure of either of its corresponding remote interior angles. So given angle 1 is an exterior angle of triangle MNO, prove that the measure of angle 1 is greater than the measure of angle 4, and the measure of angle 1 is greater than the measure of angle 3. Those are our two remote interior angles because they're not connected to our exterior angle. If you notice, the exterior angle and the angle right inside actually form a supplementary angle relationship. So let's go ahead and start our indirect proof. So we want to assume again, we're going to assume the opposite, that M, the measure of angle 1, is less than or equal to measure of angle 4, or that the measure of angle 1 is less than or equal to the measure of angle 3. So the measure of angle 1 is less than or equal to the measure of angle 4. So that means that it's either going to be equal to it, measure of angle 1 equals measure of angle 4, or it's going to be less than it, measure of angle 1 is less than measure of angle 4. So let's take a look at the first one. What happens if it's equal to it? If the measure of angle 1 equals the measure of angle 4, then the measure of angle 1 equals the measure of angle 4 plus the measure of angle 3. But we already said that this is equal to 4, so that would say measure of angle 1 equals measure of angle 1 plus measure of angle 3. So then therefore, the measure of angle 3 equals 0. Well, how can we have an angle of 0? Like if we have an angle of 0, then our angle doesn't exist. So measure of angle 1 cannot equal measure of angle 4. Cannot have a 0-degree angle. Okay, for our triangle. Next up, measure of angle 1 is less than measure of angle 4. This is our second case. Well, by the exterior angle theorem, measure of angle 1 equals measure of angle 4 plus measure of angle 3. So because the angle measure of the triangles are positive, the definition of inequality implies that measure of angle 1 has to be greater than measure of angle 4. So because angles are positive, measure of angle 1 has to be greater than measure of angle 4. Because if it's not, then you're going to get a negative angle over here, and that's going to break this whole thing down. So measure of angle 1 has to be greater than measure of angle 4, and measure of angle 1 has to be greater than measure of angle 3. The reason for 3 is the same thing as that we just did for 4. You can put 3 in its place and you would end up with the same result. So go ahead and go back through each of these proofs, looking at each line by line as we did it. Again, you want to start off with whatever you're given. Wherever you want to end up with, you're going to do the opposite of that. And after you've done the opposite of that, you're going to show that it will not work. And by it not working, we actually prove what we originally set out to prove.